Hi, my name is Sia Aggarwal, and this is my final Lab 6, Magnetic Molasses. So for the introduction, the purpose of this lab was to investigate different magnetic currents by observing the behavior of a bar magnet falling through a long aluminum tube. And we wanted to computationally model these interactions using the Biot-Savart law, the Newton's second law, and Faraday's law. And we also wanted to compare the computational model with our observed results. So the experimental time we got was 1.472 seconds, and the computational time we got was 1.167 seconds. And we'll talk about the disparities between these results at the end. So as I mentioned, there were three main laws that we were using to calculate these results. We have that EMF is negative n, which is the number of coils, and then the flux with respect to time. And then we also use the Biot-Savart law, which is describing the magnetic field as generated by a constant electric current. And we also have Newton's second law that the net force on an object equals the time derivative of its momentum. So one thing in this image you can see is we know from the Faraday's law, as I mentioned prior, that the induced current at the top was a loop going counterclockwise, and the induced current on the bottom was a loop going counterclockwise, and this was calculated through our math. And so we assumed that the air resistance is negligible since the magnet was heavy enough. We also assumed that the bar magnet is a magnetic dipole. We assume the only forces acting on the system are magnetic and gravitational, and we also said that friction was negligible. And these were our test results from dropping the magnet 5 times, and we just averaged the 5 times. This is my computational code, and these are the initial conditions we had where we were given a lot of these first values like the resistivity and U naught over 4 pi and G, but then we also plugged in the dimensions that we had calculated earlier. And then you can see we calculated the magnetic force from the tube on the magnet using the d flux over dt from Faraday's law. And then we also computationally determined the gravitational force on the magnet and considered that in the forces acting on the magnet, where we had the magnetic force pulling up and the gravitational force pulling down. And then we also calculated the bar magnet's velocity and position as a function of time. So this is what we got. We can see that the tube was created, and you can see the velocity versus time shows that there was almost a constant velocity through most of the fall until for the beginning and the end, and the computational results were pretty close to ours. And so this leads to some interpretations, like which color corresponded to a clockwise current and which one was a counterclockwise. And we know this from this image that the red is counterclockwise and the blue is clockwise. And we know that because it's moving down with the tube. And what would happen to the dynamics of the system if you flip the magnet around? The magnet would still fall the same way, but the directions of the two currents at the bottom and top of the tube would be flipped based on an opposing dipole trying to attract the magnet upwards, counteracting the force of gravity. And then the total time in the tube in our real-world system versus our computational system were very close, but they were very close, which is indicative of the validity of Faraday's law and the Biot-Savart law. And then the shape of our velocity versus time plot tells us about the forces acting on the bar magnet, and we know that the gravitational force is greater than the magnetic force when the magnet enters and exits the tube. As you can see, there is a net force as the velocity is not constant, but they're equal inside the tube, which is why the velocity is constant for that time in the tube. And then friction was considered negligible, which could be a potential error, as in real life magnet was in contact with the sides of the tubes on the way down, and the measurements once again are not completely accurate, and air resistance was considered negligible, which would also not be true in real life. So what if the resistivity of the conductor were reduced to 0? The dynamics would change as Ohm's law says decreasing resistance would increase the induced current. And if holes were cut into the tube, this would mean there was less current within the tube, so the magnet would take less time with the lesser magnetic force. Thank you.